In this video, we will be discussing Hooke's law, but before we can begin talking about Hooke's law, we have to review what the elastic force is. Elastic force we abbreviate as Fe. It's a force that works to return a distorted object to its equilibrium or rest position. We have lots of different examples like elastics, springs, bouncy balls, even trampolines and hockey sticks count. So when we talk about an equilibrium position, this is a spring that's in equilibrium position. Then I can provide a force to stretch it out, and the force that's needed to return it back to its equilibrium position is what we call the elastic force. There's a potential force stored inside the springs that will return it back to its original equilibrium position when I let go. So now on to Hooke's law. Hooke's law states that the amount of restoring force, or Fe is that elastic force, is proportional to the amount of distortion. And we can write this in a really simple formula. Fe, the elastic force, is equal to K times delta X. Now note, this is a lowercase k, and this is something that's new to us. This is something that we're going to call a spring constant. And the spring constant is just how stiff the spring is. We're going to use the units of newtons per meter. So here I have the two springs. Here's the one we saw earlier. And I can pull at a certain force and it lets go and it goes back to its original position. It's not a very stiff spring. On the other hand, I have this stiffer spring which takes a lot more effort on my part to stretch out and comes back with a lot more force because it has that stiffer spring constant. Things with higher spring constants, well, a hockey stick is going to have a much higher spring constant than a typical spring. The distortion is our delta X. We are still going to use our unit of meters for this. That hasn't changed. Anytime you see delta X, we will use our meters. Now here is something I want to point out about the units. So if we plug in our units for K, which are newtons per meter, and then multiply by our units for delta X, which are meters, what's going to cancel out here? Well, the meters, of course. And what are we left with? We're left with this Newton value. And surprisingly enough, we're looking for a force. And of course, our unit for force is newtons. So that's how the units work out. So let's try a few examples just to see how easy Hooke's law can be. So here's example 1. A student stretches an elastic band with a spring constant of 50 newtons per meter by 15 centimeters. How much force are they applying? So we have three things of interest here. We have a spring constant, so we have that K value of 50 newton per meter. And then we have our distortion. We have a delta X. Now in the problem it says 15 centimeters, but on the previous page we said it has to be in meters. So we need to convert. It's a really easy conversion. We know that this is going to be 0.15 meters. And we're going to be looking for that elastic force. And we know the unit is in newtons. So if we write our basic formula down, Fe equals K times delta X, we just plug in our numbers from there. K is 50, and our delta X is 0.15. We can plug that into our calculator, which I have right here. 50 times 0.15, and that should give us 7.5 newtons. And that is our elastic force for this elastic band. Our next example is with that hockey stick. Now, this is something new that I learned this year, is that hockey players actually will hit the ice and bend their bend their stick back before hitting the puck. So it builds up the energy inside the hockey stick. So here we have Al McGinnis. He's a retired Canadian hockey player. He's going to use a wooden hockey stick with a spring constant of 850 newtons per meter. What is the distortion on the stick if he exerts 525 newtons while taking a slap shot? So a slap shot is one of the most powerful and fastest motions in all of sports. So we're looking for a distortion. How much is that hockey stick actually going to bend? So they did give us K. Typically you will be given K. Sometimes you will be asked to calculate it. Most of the time you're given it though. And we know our elastic force is 525 newtons, and we are looking for delta X. And delta X, we don't know what it is, but we know it's going to be in meters. So if we write our original formula out, and from here we're going to rearrange. So to get delta X by itself, I'm just going to divide both sides by K. So I've got the elastic force divided by K. Plug in your numbers. I'm going to have that 525 on top and the 850 on the bottom. And let's see, I got 0.62 meters. So this hockey stick is actually going to bend more than half a meter before actually ever hitting the puck, which is pretty interesting. But that will be our final answer, calculating for the distortion. We're going to take it one step further. We're going to look at one last problem that doesn't ask for anything in the original equation. Here we have a 65 kilogram girl who's sitting on a redneck slingshot. If you've never seen a redneck slingshot, I strongly encourage you on your own time to look up a video of it. It's quite hilarious. They attach a giant bungee cord to strings and they pull a seated person or someone strapped on and pull them back with a four-wheeler. It's quite entertaining. So this particular slingshot has a spring constant of 10.5 newton meters, or newtons per meter. If the sling is stretched by 45 meters, what is her initial acceleration when released? So we have our traditional spring constant and our typical distortion for a problem, but they also gave us a mass and they're asking for acceleration. Okay. The key here is that this is an initial acceleration, so we're going to look at the forces right as she is released. Remember, if we have an acceleration, we have a net force. If we have a net force, we should probably draw a free body diagram. So we're going to have this poor 65 kilogram girl sitting somehow on the slingshot, and there's going to be an elastic force that pulls her back. So when we go to write our F net equation, we know that it's just going to be equal to our elastic force. But according to Newton's second law, F net is also equal to mass times acceleration. So not only does that allow us to include this new information of 65 kilograms, but also to find that acceleration we are looking for. From there, we can substitute in K times delta X for our elastic force and set that equal to mass times acceleration. Solving for acceleration, we're just going to divide both sides by m. So we're going to have K times delta X over m. So there's our formula, but now we need all of our numbers. Well, from the problem, we know that K is 10.5 newtons per meter. We know that delta X was 45 meters. And we knew that the mass was 65 kilograms. And our units for acceleration haven't changed. We know that we'll end up with meters per second squared. So our acceleration will be equal to 10.5 times 45 divided by 65. You don't have to worry too much with parentheses in your calculator for this, but if you want to put the top numbers in parentheses, then divide by 65, it'll ensure you get the correct answer. Okay? So I have us finding an acceleration of 7.3 meters per second squared.